Yeah, yeah. So in 2022, I saw Mark Brooker give this talk, Formal Methods Only Solve Half My Problems. He published a blog post about this too, and he said that TLA Plus can check correctness, um, safety and liveness, but not performance characteristics. And quote, what I want is tools that do both, tools that allow development of formal models, and then allow us to ask those models questions about design performance. So he agrees that correctness is important, but it's not just enough to say that nothing bad happens and something good eventually happens. He wants to know how soon does something good happen. So how would we actually create a tool that does these kinds of things? Mark said that queuing theory was the kind of math that would be obviously useful for this. So I decided to learn queuing theory. I asked Mark what book I should read, and he suggested this, Performance Modeling and Design of Computer Systems, Queuing Theory in Action. The title sounds like it's the perfect kind of book for this. So I recruited Andrew Helwer and Murat Demirbaş to read it with me. We spent 8 months. We read most of the book. We did a lot of the exercises. It was definitely interesting, but mostly irrelevant to the problem of actually performance modeling and design of computer systems. An example of a queuing theory problem, here's a diagram from chapter 2 of the book. There are 3 servers, and each has a queue. Tasks can arrive at the queue. Each server processes tasks, and then the tasks either leave the network or they go to other servers. And there's probabilities of any of these events happening. What kinds of questions can we answer about a queuing network like this? So in the book, one of the exercises is a classic queuing theory problem, which is what is the maximum arrival rate at server 1 that this system can handle? That's a practical kind of question, which I solved in an impractical manner. I, with paper and pencil, modeled this as a series of equations and solved for a variable. I found that maximum arrival rate was 5.2. I don't think that we should try to answer performance questions by writing equations and solving for a variable. It's hard to get right, it's easy to get wrong, and you have to recalculate everything if any of the inputs change. I think we should just use simulation. Run an experiment thousands of times, take the average. Call that Monte Carlo simulation if it makes you feel less primitive. There's an open source tool for doing this called the Java Modeling Tools, JMT. It's a bunch of tools, and you can model queue networks and simulate them to come up with answers for these sorts of questions. So I took the exercise from the book and I turned it into an extremely ugly JMT queuing network. And what? Yeah, that's right. Exactly. Java. It's ugly to write. It makes ugly UIs. I asked it, what's the max arrival rate here? And I configured a bunch of things. I configured a simulation. JMT lets you sweep a variable. So I swept the input rate from 0 to 10 by increments of 0.1 over there. And so that's the independent variable. The dependent variable is what's the server utilization of server 1. And as you can see, when the arrival rate hit 5.2, the utilization hits 1. We now know that the system has maxed out, and that's the same as the answer I got with paper and pencil. This kind of simulation works even for very complex queue networks where the math is difficult or actually impossible. So what I've learned from the book and the tool is that queue theory has super useful concepts: arrival rate, service rate, utilization, ergodicity. But the math is heinous. There's some simple equations like Little's law, and then all hell breaks loose. So don't try to learn the math. It doesn't matter how good you are at math. It's not going to get you what you want. You cannot estimate system performance by solving equations. So just run simulations. Now, if we have a tool for simulating queuing networks, does that solve all of Mark's problems? No, because Mark wants tools that do both formal methods for safety properties and also performance modeling. How do we have a single syntax that does both? So the same year that Mark talked about this, Marcus and Jack Van Lightly presented obtaining statistical properties via TLC simulation. And I'm going to show some code examples from Jack's spec for a gossip protocol. So Jack's spec uses TLC set to record each statistic. Like here, it's counting the number of times that a node has gotten new information. TLC set and TLC get are accessing a global scratchpad without affecting the state space. So you can record things. And what you're recording here is called a cost function. It's some thing that you want to measure about the performance of your system. This code appends a line to a CSV file to output some of these statistics so they can be analyzed in other tools. Jack had to hand code all of this. He had to hand code the condition for when it's time to actually run this line. It's impressive that it works at all, but it's kind of a hack. So my complaint number one is the syntax. What we have now in TLA Plus, it's hard to write, it's easy to get wrong, and it clutters up the specification. Here's some code to determine probabilistically whether a message is lost or delivered. Jack has a config option called message loss mode. It can either be probabilistic, in which case statistics gathering works, or it can be exhaustive, in which case model checking works. So my complaint number two is that randomization and model checking are incompatible. If message loss mode is probabilistic, then here's some code for deciding whether to lose a message. And then there's another config option, config lose nth. If that were, say, 4, then there would be a 1 out of 4 chance that a message is lost. You could extend this to any rational number, like 2 out of 3, but it can't be an irrational number. You can't just choose any floating point number. So my complaint number 3 is that randomization is very limited. It's basically just a Dungeons and Dragons dice throw. And if you want to measure performance, you need some sort of cost function, like let's say sending a message to Tokyo costs 2.5 times as much as sending it to London, or maybe the cost of a message is exponentially randomly distributed. All the examples I've seen of TLA Plus with statistical properties are counting discrete events that are all kind of the same. If we want to measure the performance of a system as a whole, we need cost functions for a variety of events that are going to have relative costs that are going to be randomly distributed. So my complaint number 4 is that we've got no floats. We've got no probability distributions besides uniform. So I think that this was a really cool start, despite my complaints. Like, it started a conversation that I'm now trying to continue, which is, are we serious about statistical properties? Should we try to solve both Mark's problems with the tool that we've got so far, or should we just stay focused on safety? I don't know. I haven't implemented anything. I'm just offering ideas. And I want to admit that I'm not currently offering to invest time or money in this, so I can't make any demands. I'm just brainstorming with you. I'm going to start brainstorming by reviewing 4 state-of-the-art tools, at least that I found in my research. One is JMT, and then there's Prism, Runway, and FizzBee. So JMT, as we saw, comes with an extra L straight from London, tariff-free, and it's made for solving performance modeling problems. and answering performance questions. It's got a point-and-click interface. You could consider this a pro for small networks and bad for big ones, but there's also a Python API for constructing them en masse. It comes with lots of probability distributions. It understands cost functions, and you can use real-world data sets as inputs. So if you've measured the histogram of message loss or message delays, then you can input that, which is cool. Moving right along to state-of-the-art number 2 is Prism, a probabilistic model checker. Hillel and Andrew have written about this on their blog, so you've probably read about it. You write a spec of an algorithm and you ask statistical questions like the probability of something happening or the cost of something. An example of its syntax, here's an action with a name. It's got a guard, which is some sort of predicate. This action is enabled if x is 0. And then some updates that you can make in the probability of each. So there's a probability of 0.8 that this action will set x to 1. There's a probability of 0.2 that it will set x to 2. These probabilities are rates also, depending on whether this is a discrete or a continuous model. Prism has cost functions. Cost is just anything that you want to measure, any way of expressing performance. Prism calls them rewards, but if you're thinking of reinforcement learning, don't. This isn't about that. This is performance modeling. This code from Prism says that as long as x is 0, the reward is 100. If x is between 0 and 10, then the reward is 2x. It's just an example of how expressive reward functions are. You could imagine writing a reward function that measures revenue or a bad cost that's called a reward like latency. Prism has really powerful property expressions. Here's an example from their website. It's the probability that more than 5 errors occur within the first 100 time units is less than 0.1. So this is an assertion that you can check with Prism. You can also ask a question like, what's the probability that process 1 terminates before process 2 does? And then Prism will answer that question for you. You could express safety as saying that the probability something bad happens is 0, or liveness as the probability that something good happens is 1, or a much more sophisticated performance property like what's the 95th percentile latency, assert that it's less than some acceptable value. Prism has a bunch of great examples on its website, the result of, I think, decades of development. Here's statistics from a Prism model of a gossip protocol. As nodes discover each other, the paths between them get shorter over time. Making charts like this is a built-in function of Prism. It's made for this. But Prism can only express models that are simple enough for Prism to calculate performance by solving equations. That means that basically it's only got scalar variables with floating point values. It's got no sets, it's got no arrays, no hash tables. And that makes Prism specs kind of awful. Here's part of the gossip protocol. So it's got 4 nodes, and for every node, whether it can see one other node is 1 variable, so there's 16. If you had 5 nodes, you'd need 25. The more nodes you have in this spec, the more code you need. Here's node 1's code for talking to nodes 2, 3, and 4. You'd have to add more lines if you had a 5th node. There is no generic programming whatsoever. Node 2 has the same code as node 1, which they accomplished by just like horribly renaming all of node 1's functions as node 2's functions. This is an abomination. This is banned by the Geneva Convention. Some grad student was found lying, drooling on the floor after writing this. I mean, actually, it was probably just generated by code in some other programming language or an Emacs macro. Like, Prism is a assembly language for expressing Markov chains, which Prism then solves. But it's obviously not a good language. It's Markov chain based. Is that different? It's an automaton? Okay, thank you, Andrew. Moving on to state-of-the-art 3, Runway. So this is by Diego Ungaro. He published Raft in 2014, and then he announced this cool thing 2 years later, but then he stopped working on it the same year. But it's got good ideas. It's got a very familiar syntax for programmers, and it's got randomization built in. If Runway is in model checking mode, it somehow tries all the possibilities, and if it's in simulation mode, then randomization just picks one value the way you would expect. Whereas we saw Jack's TLA plus spec had to sort of code around the problem of randomization versus model checking. This does it automatically. Marcus.
Yeah, to that, I think that's a little bit outdated because as part of working on the talk, we built that into TLC, that there's a probabilistic mode and an exhaustive mode now. So that one complaint, I guess, can be scratched, but the other ones are fair.
Thank you. Good. Runway has visualizations built in to some extent. I think that this elevator simulation on the left required a lot of manual coding, but the chart is a built-in aspect of Runway. So if we wanted to do something like this in TLC, I think that making charting like this convenient would be something that would be easy and obvious for us to do. The final state-of-the-art thing is FizzBee, developed solo by JP, whom a lot of us know. Here's an example FizzBee spec from the docs. The spec describes a service that can look up some data. First, it checks in a cache. If the cache misses, it looks up in a database. The lookup action's defined here, and it calls a lookup cache function. And then over here is this separate config file just for performance modeling. And this separate config file defines the cost of calling lookup cache as 10 milliseconds of latency. The lookup cache function is non-deterministic. It either returns hit or returns miss. And these two possibilities are labeled. And then back over here in the config file, the probabilities of those two actions are defined separately. I think this is really nice how performance modeling doesn't clutter the spec. If you run FizzBee's performance modeler, it will tell you the average latency. And it will also tell you that the lookup function returned hit 20% of the time, found 72% of the time, not found 8% of the time, which makes sense given the probabilities of those actions. Back over in the config file, you can see that a cost doesn't have to be a constant. It can also be a probability distribution. FizzBee allows any probability distribution supported by SciPy, which is basically all of them. Or you can bring your own histogram, like with JMT. You can use some experimental data as an input. Yeah, going back to what Mark wrote, he wants tools that allow real-world data to be included in performance modeling. FizzBee and JMT allow that. I think FizzBee's design is really smart. It built in a lot of important ideas like cost functions and probability distributions, probabilities of state transitions. We don't have to write a lot of error-prone code to make performance modeling work in the spec. And I think it's really nice how it separates out performance modeling config from the main spec. This is a lot like we do in TLA Plus, where we try to keep model checking stuff out of the main spec. FizzBee allows the same for performance modeling. I I don't know how much of this is actually implemented versus examples in the docs. JP has been working solo for a couple of years, but we're just interested in the ideas here, and I think that these ideas are good ones. So what we've seen so far in those 4 state-of-the-art thingies, I will bucket to 3 buckets. Under expressivity, we want to be able to annotate state transitions with probabilities, define cost/reward functions, use Prism's powerful property expressions. Runway and FizzBee permit model checking to be compatible with performance modeling, which we do now with TLA Plus as well, floating point numbers. It's really nice to have common probability distributions built in and to use experimental data as well. And of course, we need some sort of solvers to actually answer the questions that we can express with the syntax. Nice to have a separate config file for performance modeling. And it would also be nice if charts were convenient. So now comes the part of the talk that I dread the most, where I propose a possible syntax. This is also the least important part of the talk. So maybe I'll just like hold it up as a hold it up as a target to draw fire. So every place that we have non-determinism in a spec, like here, we need to somehow give it probabilities. So what if we wrapped sets or sequences in some sort of operator that we named? We could call it message loss probability here. And when model checking, it's non-deterministically false or true. Or this could be a label for a probability distribution, which we then define in a config file. So here in the config file, that could be a built-in or user-defined thing called a Boolean choice, where it's like true 0.23% of the time or whatever. We would also need cost functions. Those could just be every action has a cost associated. And so you could define that down here. You could say that the cost of send message is some exponential distribution or whatever distribution you want to use. And you could also bring your own histogram here. Just an idea. We should also actually be able to answer questions that we ask. So we'll need some sort of solver. And in order of ambitiousness, you could just use the generate TLC option that Marcus showed, generate thousands of behaviors and take the average. You could use generate and run stats until they stabilize to within a certain precision. This is what JMT does. And maybe you could also be smart about like regions of the state graph that stabilize earlier than others, so you could guide your exploration. You could just use Prism solvers. This was Andrew's idea. Just generate a state graph, translate it to Prism, and then, or something like that, use Prism's decades of research into solving Markov chains to solve our problems. Or we could write a solver or solvers from scratch and hook into lots of research into finding stable probability distributions for Markov chains. If we did this, would it be cool? It might be. One model could express an algorithm. We could check correctness, but we could also evaluate the performance. We could simulate what-if experiments by bringing in real-world data and seeing how an algorithm would perform given those inputs. It would let us confidently explore optimizations by both checking that they don't break our safety guarantees and that we think that they would make things go faster. So that's what I got. Thank you to the following people for helping. And I'm not going to take questions because I won't be able to answer them. So instead, I'm going to ask you questions, which are up here. Thank you very much.
Okay, this is on. Maybe we take 2 or 3 minutes for questions or answers rather.
Correct.
And then we have a coffee break. But yeah, something top of mind.
take the fourth one.
Okay.
So, okay. I've been working on exactly the same problem for several years, not in the context of TLA plus, but for sense, basically checking both correctness and performance products distributed systems, which I think is a very important problem. It was emphasized by Amazon Web Services a decade ago in the 2015 famous paper called "How Amazon Uses Phone Methods," right? So, I think probably, for example, the Prism or maybe other automata-based tools, they use probabilistic model check, which also suffers from the state space problem.
Right.
So I recommend statistical model check, which is a black box check. Which doesn't suffer from the state space problem, but of it can only give you the answer with some statistical confidence.
Right.
For example, questions like 99% of the confidence the system satisfies probability with some probability, right? Okay. And yeah. So another one. So in my opinion, I think apart from also the question like the probability of satisfying some, which for example could be like let's say Cassandra they claim to satisfy the eventual consistency, right? But in practice, it actually achieves a stronger guarantees. So you can answer question like with some probability, Cassandra can actually achieve strong consistency, for example, right? Apart from that kind of property, people also care about throughput and latency, which is real value properties like the throughput of the system.
Yeah.
Especially if you compare two algorithms, you want to see the trends of the curves of the throughput, right? So so that's beyond the probability of the probability shows like you can express the probability of some. So that's I think that's relevant to the expressness of the property. In terms of I think for TLA pass you also need to consider a specification for some logic to deal with real value property. So yeah.
Thank you.
Thanks. I would also like to take a stab at least one or two questions. Let's start with number 6. I think resounding yes, which leads me to question number 5. Yep, the TLA Plus Foundation should get funding for this, especially because I believe that technical solutions are not that hard.
Right.
There's already quite a bit in TLC, also because it's technically related to simulation. In the simulator, we have the same problem. Right now, we're essentially naive random exploration, right? And obviously, like with the terms we heard earlier, you end up usually generating just new states where the term keeps increasing towards infinity. That's boring. So those two are intertwined. Want to kind of probably use the same solutions. So now the question 5A is, who is going to join the TLA Plus Foundation as the next member in order to fund this kind of work?